The galaxy has many stars orbited by many planets, and many of these are orbited by immense icy moons. But could others have oceans on their surface, or even life? In the early 24th millennia, a colony Ark fleet arrived around Cygnus X1, a black hole supergiant binary 7,200 light-years from Earth, where they had used the black hole to permit them to decelerate down from a high fraction of light speed. This had become a common way of seeding regions of the galaxy to send out massive fleets propelled by enormous pushing beams to distant black holes, where they could use the powerful gravity of the object to slow down with little to no fuel. Of course, a black hole orbiting very close to a blue supergiant just waiting to go bang is not an ideal place to set up your civilization, and a rough place to break a fleet at, so they planned to complete their maneuver, then drift over to a nearby system in which Astrius, a G1 sun just a bit brighter than our own, was orbited by some planets, including an immense gas giant named Zephyr that dwarfs even Jupiter. From here they would set up their alpha base, where they could resupply, and from which splinters of the fleet could radiate out from this new hub of humanity's galactic expansion. As the vanguard of the fleet completed their maneuvers around Cygnus X1 and left the region of massive radiation and lighting around the binary, they turned their telescopes on the Astrea-Zephyr system to learn more details of its minor planets. They soon saw a beautiful oceanic moon around Zephyr, which they nicknamed Aquarius. Aquarius orbited Zephyr at roughly the same distance Ganymede does Jupiter, but even though Zephyr is roughly the same size as Jupiter, it's more than 20 times as massive, and Aquarius orbited it a bit less than once every 24 hours. With its atmosphere protected by Zephyr's powerful magnetosphere, Aquarius is also warmed by a strong mix of light from Astrea and tidal heating from Zephyr. It was, in short, a very plausible place where life might have emerged. The journey to Aquarius was next to nothing compared to the journey Cygnus had been, of many thousands of years, but would still give them much time to speculate about the growing mysteries of Aquarius. While speculation about Aquarius was rampant, most did not expect to find anything beyond perhaps simple life there, or perhaps semi-intelligent animals, as other expeditions had reported occasionally in the past 20 millennia of interstellar exploration and settlement. And yet, once they arrived and sent down robotic probes, they found an ancient civilization that had evolved beneath its turbulent waves. The civilization of Aquarius, named simply the Aquarians until such time as their own name for themselves might be discovered, had begun in the abyssal depths, where light from their parent planet and distant sun barely reached. Aquarius is quite massive for a moon, more than any moon in humanity's original solar system, and yet still far beneath that of Earth. As such, its gravity is lower, and the pressure rises more slowly with depth. The Aquarians were beings of incredible intelligence and adaptability, evolving from simple bioluminescent creatures into complex sentient beings, capable of thought, emotion, and intricate communication through patterns of light and sound. Their bodies were sleek and adapted to high-pressure environments of the deep sea, with large eyes to capture the faintest glimmers of light and limbs that could manipulate their surroundings with precision. The Aquarians developed a society that was harmonious with the ocean, building structures that floated in the dense waters and harnessing the energy of thermal vents to power their emergent technology. Technological progress was a slow thing, though, with no fire to help them and prod on discovery. They recorded their history by carving it into stone and dated it by their seasons of over a decade in which Zephyr orbited Astrea, and the number of those seasons recorded in the tens of thousands. As millennia passed, the Aquarians explored every crevice of their underwater world, discovering the ruins of an even older civilization that had once thrived and then vanished into the depths. With the help of their new human friends, who appeared to them merely as sleek artificial probes, they were able to determine that those ruins were of a prior civilization that lived in floating rafts, destroyed over 1 million years ago by a supernova in the region, which they think might have sterilized all the life near the surface and melted the small polar ice caps, which were just beginning to reform in recent millennia. The first Aquarians escorted to the surface to see their night sky went at night to help protect their vision, designed for the darker ocean depths, and at first, even knowing better, they thought Zephyr must surely be this bright sun they'd been told of, for it glowed far more brightly than Earth's own moon and dominated the sky, hundreds of times larger than our own moon, if dimmer in its reflected light for its size than our moon, being further from Astria. A translation of their elders' first comment after seeing was later carved into the commemorative plaque on that first floating spaceport. "I wish our eyes were built like yours, friends from the stars, for surely such an awe-inspiring first glimpse deserved tears of joy." They had no name for Astria or Zephyr till then, and so they kept the one their visitors had given them. The Aquarians were quite bright and peaceful, and a deal was struck quite rapidly with their human visitors to permit complimentary settlement of this region of space in exchange for assistance uplifting their civilization's technology to permit both surface settlement and space travel of their own, and logistical aid finding and settling their first handful of colonies. In truth, though, both the Aquarians and humans were more fascinated by finding and exploring those ancient ruins on Aquarius to see if it was the remnant of an order branch of their species, or possibly some outpost or settlement from some other visitors. The news of all these great discoveries would take tens of thousands of years to percolate out to all of humanity's ever-growing presence on the galaxy, and perhaps in time, word would come of other worlds with other civilizations upon them. And so, the civilization of Aquarius rose from the depths of their oceanic world to become explorers of the galaxy, leaving a legacy that would inspire countless others to look beyond their horizons and to wonder what lies in the uncharted waters of space. Of course, it has reopened the argument of what to call a body orbiting a substellar object like Zephyr. Is Aquarius a moon or a planet? And should the Aquarians be consulted for their preferences on the matter? The sun and moon have dominated our night sky and our thoughts of space since the dawn of humanity, and yet other civilizations might arise on large moons around even larger planets. We talked about trying to settle icy moons of gas giants like Europa or Ganymede around Jupiter, or Titan orbiting distant Saturn, but today we'll be zooming in on moons big enough for oceans, and not simply subsurface oceans, but also like those we have on Earth, open to sun and sky. The story of moons like this is very different from Earth's own, or those moons around our own gas giants. It's a place where the moon doesn't need its own magnetic field to keep an atmosphere, because its parent planet has a field so immense it wraps it in a protective shell. It's one that doesn't need the gravity a full planet has for that either, because it gains so much of its warmth from tidal heating that it doesn't need as much from its sun, and the powerful solar wind and radiation inbound from that sun is diminished by the extra distance. And yet it is one on which life might easily arise in the deep seas, with a world shorn by even more powerful tidal forces than those Earth experienced during the time in which we believe life might have arisen around thermal deep sea vents. Whether or not that's how life arose on Earth, it's certainly a plausible mechanism for life arising on another world, and we shouldn't assume what happened here is the normal way it happens everywhere, let alone the only way. We tend to assume if you got a decent energy flux through a place where the basic building blocks of life can be present in high density, and in a decent chemical solution like water or maybe ammonia, that you have a chance of getting life. Volcanic thermal vents on the ocean floor are a great option for that, so are tidal pools, or drainage basin lakes where something like phosphorus might accumulate in quantity. So too are comets. Panspermia remains a distant runner-up to those other mechanisms, but still is in the race. And what's interesting is that all of those options are either just as probable on oceanic moon of a large gaseous planet, but arguably stronger factors than on Earth. And one critical thing about moons is that while they tend to be tidally locked to their planets, not only might this not be the case for a moon with deep seas and atmosphere around a very large planet, but it doesn't result in the eternal night and day sides we get with a planet tidally locked to a star. Of course, a lot depends on what we are calling a star here too, or a moon, because the dynamics are very different if we're considering a body orbiting a substellar object like a brown dwarf, too small to be a true star, but too large to be thought of as a true planet either. And these substellar objects likely are as numerous as the stars themselves, maybe even more so, which is important to keep in mind as we contemplate life emerging on them. It is possible such a world, like Aquarius, might not even be tidally locked, for the force of gravity that slows such worlds down till their rotational rate matches their orbital period does so by acting like a brake on a wheel, and if you grease that with seas and sky, that process should slow greatly. It's also powerfully controlled by distance, and the orbital distance that a substellar object could keep a large moon stable at is closer to that of a star than a planet. For ease of calculation, I treated Zephyr as 25 times more massive than Jupiter, about double the minimum to be a brown dwarf, but only a third the minimum to be the dimmest of red dwarfs. Your orbital period, when discussing a smaller object orbiting a much larger one, goes with the inverse square root of mass, so 25 times the mass, 1/5 the orbital period at the same distance, 100 times the mass, 1/10 the orbital period. Zephyr is 8,000 times more massive than our Earth, so something orbiting as far away as our moon orbits us would do it about 90 times faster than our moon, a few times a day rather than once a month. Looking from the other perspective, it's only about 1/40th the mass of our Sun, meaning things at the same distance take 6 to 7 times longer to orbit Zephyr than our own Sun, also called Sol. In Zephyr's case, we intentionally place the world at Ganymede's distance as it orbits Jupiter every 172 hours, a little over 7 days, so would orbit Zephyr at 1/5 that, 34 hours. If Zephyr were 50 Jupiter masses, it would be a 24-hour day at Ganymede distance. Jupiter and Zephyr would both look the same size in the sky at that distance because gas giants and brown dwarfs are all about the same size, they just grow denser. At a certain point, dense enough to ignite true fusion and become a red dwarf. Jupiter is thrice as massive as Saturn, which is itself the least dense planet in our solar system. Earth is actually the densest, but while thrice as massive, Jupiter is only 20% wider and 73% greater in volume than Saturn. The brown dwarfs we found were all of a similar size to Jupiter, just denser, and even the smallest red dwarfs, M9 main sequence stars, are only about the size of Jupiter and about 1/10 the radius of our own Sun, while being 1/10 its mass, so 100 times denser than our Sun or Jupiter on average, which are fairly close in density. Basically, the density of gas giants, substellar objects, and stars begins rising sharply after Saturnine masses and peaks for red dwarfs before dropping again in larger stars. The heat of fusion in their core begins fighting back against gravity, boiling that star, so to speak, and pushing it apart. Every star reaches a balance point based on its mass and composition, and we call this hydrostatic equilibrium. This matters for moons because it means they can be close enough to these titanic bodies to get periods of a day, thus letting them be tidally locked and yet Earth-like if their planet orbits a sun. And yet they could be further away and still enjoy the protective magnetosphere of the host planet, or substellar object, as well as tidal heating. Today we'll also explain the mechanics of tidal heating and tidal locking for that matter too, though we've covered that in more detail in past episodes, so we'll give it a lighter treatment. For today, we will also assume something orbiting either is a moon, and refer to brown dwarfs as planets when they are orbiting a star, simply for ease of discussion. Now, why the focus on oceans? Partially because even though the magnetosphere of that big planet might shield the moon, you might still have some radiation coming in that might be rough on life not protected by a thick hide or a couple inches of water. Indeed, in some cases, the radiation might still not allow any surface life, land or sea, with everything keeping itself tucked just a little under the water where light could still usefully reach for photosynthesis. But that's not our main interest in oceanic moons. It comes down to our case where a planet is getting a large mix of its energy flux from both tidal heating and sunlight from the star the planet is orbiting. Water is less common in our inner solar system because while both hydrogen and oxygen are abundant, hydrogen tends to get pushed out by the solar wind. Once we get deeper out in space, objects with vast amounts of ice get far more common. Jupiter's own moons have tons of ice, and we also believe there are large subsurface oceans, thawed out by Jupiter's tidal heating and insulated by that ice layer up top. It does not seem too much of a stretch to assume we could have a bigger moon that got more sunlight than the Galilean moons of Jupiter, but was shielded by distance and their planet's magnetosphere from the hydrogen stripping effects of its sun. and so it seems fair to assume a moon warmed by a gas giant could have surface water, and because it would have begun its existence with a far higher ratio of water to rock than we have, it would be quite likely it would have less land than us, having deeper oceans that any volcanoes would have to rise above to create surface land. Possibly no dry land will exist as a result. It's really hard to say as we don't know enough on the matter yet, and it would probably depend a lot on the gravity of that moon too. Such moons may have no land area or limited archipelagos, and may have ice caps and icebergs floating around or not. In the case of Astrea, our G1 sun Zephyr orbited with, or was binary to, assuming it was a main sequence star, it would be about 20% to 30% brighter than our sun, and a few percent more massive, and thus only have a habitable zone about 11% to 15% wider, and with fairly parallel orbital periods. I placed Zephyr out at a more Saturnine distance for our tail to make its surface light from Astrea a much smaller factor in its energy and less important for life evolving there and shifting to the surface. But if Aquarius was as close to its sun, Astrea, as we are to our own, 1 AU, or astronomical unit, then it would probably be too hot, even ignoring the tidal heating. But how much is this tidal heating? People talk about it a lot but rarely give much math, including myself, and while the math is only an approximate model, it's not a very complex equation, so let's walk through it briefly. Let's start with a point of reference though. Earth gets 3.7 terawatts of tidal heating, 3.2 from our moon and 0.5 from our sun, or about 85% and 15% respectively. And yet that only makes a minuscule fraction of our energy, as again we get 3.7 terawatts from tidal heating, but a whopping 173,000 terawatts of solar energy striking Earth from the sun, almost 50,000 times as much. We'd have to be over 200 AU from the sun before tidal heating we got from the moon matched the influx from our sunlight. That's more than 5 times the distance to Pluto and nearly double the distance to our furthest known dwarf planet, 2018 AG37, also known as Far, Far Out. So what are the factors for tidal heating that let us talk about warming a planet's moon? Well, we may think of this as the energy of tidal friction that's working to tidally lock that object, or which is grinding on it as it moves from its closest to furthest point of an elliptical orbit. So we should not think of it as a constant force on geological timelines, but then neither is the luminosity of stars. They brighten as they age, though they are bright early on when in their protostar phase, even if that's getting absorbed by all the remaining gas and dust of formation that is now blowing away from itself and its newly minted planets. And that's from the heat of gravitational collapse, which all the planets and moons have too, and from which they slowly cool, while internal pockets of radioisotopes decaying and tidal forces work to keep them warm. For an already tidally locked moon, this tidal heating is coming from that elliptical orbit, and rises with a square of eccentricity, which is a number between 0 and 1, where 0 is a perfectly circular orbit, and as you rise toward 1 it grows more eccentric, the ellipse more stretched out toward eventually a parabola instead. Double your eccentricity, quadruple your heating, triple it, 9 times as much, etc. And ignoring other factors like other moons or planets, this will mean any moon around a planet or planet around a star will grow more circular in its orbit with time. The other 2 factors I want to note are the radius of the satellite and its orbital period or distance. The 2 are interchangeable for a primary of the same mass, so we'll go with the period as more intuitive. The bigger the radius of the satellite, the more bits of it get yanked relative to each other because it's wider. To explain that, a moon orbiting a planet might have the side near the planet experiencing 1% higher gravity than its center does, and the far side about 1% less, meaning the near side gets yanked on a lot more, and also being bigger, there's more of it to yank and heat up. The closer it is to that planet, the stronger the effect, or, as an alternate way of viewing it, the more frequently it orbits that planet, the more times it's getting yanked on. Again, that's an intuitive explanation. Mathematically, it means that while heating rises with the square of eccentricity, it also rises with the 5th power of that moon's radius, and drops with the 5th power of its orbital period. We're skipping discussion of the Love number, density of bodies, uniformity of them, or the radius of their parent planet, and at least in the last case it doesn't vary with bigger ones since they're all about the same size as Jupiter. Our moon is a quarter of the radius of Earth, so an Earth-sized moon, all things being equal, is getting 4 to the 5th power more heating, or roughly 1,000 times more. And to emphasize how big a factor something raised to the 5th power is, something twice as wide as the moon will get 32 times the heating, not 1,000, while something twice as wide as Earth will get more like 32,000 times the heating as opposed to 1,000. And right there would result in the huge difference between solar heating and tidal heating we noted on Earth, where it was 173,000 terawatts versus 3.7, a difference of almost 50,000. On the flip side, the longer the period of orbit around that primary, the less that heating. So for our case of Aquarius orbiting Zephyr at the same distance Ganymede orbits Jupiter, but 1/5 the period from Zephyr outmassing Jupiter 25 or 5 squared as much, meaning it is getting 5 to the 5th or 3,125 times more tidal heating than Ganymede. Throw that in on a bigger and wider body, and suddenly tidal heating is a very dominant factor. Those Galilean moons also tidally heat each other quite a lot, but let's ignore that for the moment to shift to another point. We're seeing that a large gas giant a bit closer to its star's normal habitable zone than Jupiter could quite possibly have a big warm oceanic moon on it from a mix of tidal heating and sunlight, where neither might otherwise be sufficient, but that's heating pre-tidal locking. Moons take a while to lock, all the slower when bigger or further from their planet, and stars also warm with time, so we could have some interesting cases of increasing sunlight replacing diminishing heat from tidal locking to keep a moon on the warmer side, all within a typically high water content from what we'd expect from a totally sunlit object of the same mass and temperature. Now, when it comes to tidal locking, the energy of a body's rotation and orbit is actually quite enormous. Earth's rotational energy is 214 billion joules, and used to be about 4 times higher, we think, back in the primordial days of Earth when the moon was closer and not tidally locked, which even drained out at a rate of over 100 million years is still on an order of magnitude more than our current tidal heating. But its orbital energy is around 12,000 times that high, and a larger moon of a brown dwarf could easily have more orbital energy than Earth does around the Sun. So particularly if we imagined an icy outer planet being captured by a brown dwarf orbiting a star with a high initial eccentricity, it becomes very plausible that we end with a large oceanic moon being heated by a strong mixture of sunlight, tidal heating from that giant planet, and tidal heating from interacting with their moons. The habitability of oceanic moons mostly comes down to them having energy flux, warmth, and water. The jump between a place like Europa and our hypothetical planet Aquarius is that now it can get significant surface lighting involved in biology. And again, it may not be tidally locked at all, a relatively eccentric moon in a more distant orbit, and with seas and sky, potentially several million miles from its primary, could have an arbitrary day length same as a planet can. At such distances, even a brown dwarf at the top range of mass might be no bigger in its sky than our moon or sun either. It's a funny thing about main sequence stars, their brightness rises so sharply with surface temperature that their habitable zones expand rapidly with their mass, meaning those tiny dim red ones look far larger in the skies of planets warm enough for life, while enormous giant stars actually would look like ultra-bright but tiny suns from their Earth analogs, and so things like total eclipses we have where the sun and moon are about the same size are very uncommon, while a planet closely orbiting a gas giant will get them almost constantly unless that gas giant itself orbited in the habitable zone of a dimmer red dwarf. Or again a decent way outside that habitable zone since tidal heating would move that effective zone outwards. For today, we'll skip the terraforming angle beyond saying if you got some big icy moon, one with enough mass you want to settle it, you can make it an oceanic one with orbital mirrors or Lagrange point array, and then you can add huge floating raft cities if you want, or even floating continents. You could potentially be nuking the underwater surface to spawn dry land by volcano too. The native ecology is more fascinating though, because life as we understand it requires an energy source, and while on modern Earth life relies primarily on sunlight for photosynthesis, on such oceanic moons or subsurface icy ones, life forms can instead depend on chemosynthesis, deriving energy from chemicals emitted by hydrothermal vents. Similarly, oceanic moons could have hydrothermal activity on their ocean floors, providing the necessary energy for life. With sufficient tidal heating, possibly even robustly enough for large and diverse ecosystems, they may be able to add photosynthesis to that. The chemical building blocks will all be there, and I suspect we'll find more moons that fit the bill than Earth-like planets. Their long-term stability is harder to speak to, but so long as they change slowly enough for life to adapt and move, then once established, they should be places life could dwell on indefinitely. I suspect we're as likely to encounter life on such moons as on planets we find, and in cases of those with subsurface oceans, maybe even extraterrestrial life in this solar system on Europa or Callisto. In summary, the habitability of oceanic moons still has a lot of unknowns that require further investigation. While they offer promising conditions for life, such as the presence of water, energy sources, and organic compounds, they have their challenges too, and probably many we don't even know about yet. The continued exploration of these mysterious worlds may one day answer the question of whether we are alone in this universe, or even in this solar system. I generally try to limit the math we go into during our episodes, but as we saw today, even on something like tidal locking and orbital mechanics of a moon, it can be a fairly intuitive concept, even if the math can be a bit intimidating. But math doesn't need to be intimidating. You just need good partners to help you learn it. If you got that, there's no distance you can't cover, whether it's professional growth or in your own journey to the stars. And Brilliant.org is a great place to start that journey. Brilliant helps you build critical thinking skills through problem solving, not memorizing. So while you're building real knowledge on specific topics, you'll also be becoming a better thinker. Build real knowledge in minutes a day with fun lessons you can do whenever you have the time. Learn through problem solving and doing, with hands-on interactive content that's fun, immersive, effective, and intuitive. Brilliant.org's content goes from the basics all the way up to advanced materials on math, science, data, probability, computers, and AI. Start where you need to and go as far as your dreams can take you. You can try everything Brilliant has to offer for free for a full 30 days. Just visit brilliant.org/IsaacArthur or click on the link in the description. You also get 20% off an annual premium subscription. So that wraps us up for today, but this Sunday, June 16th, we'll be looking at another place to live, and a very nice one at that, as we examine the idea of paradise planets, places even better than Earth for us to live. Then we'll ask what would have happened if dinosaurs had never died off on June 20th, and we might have seen a world with a mix of big mammals and dinos, or even if they might have developed a civilization one day. After that, we'll explore the idea of hollow planets, both notions that Earth might be one, and that maybe it will become one in the future. Then we'll wrap up the month with an examination of free will and quantum mechanics. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show by becoming a member here on YouTube or Patreon, or check out other ways to help at isaacarthur.net. You can also catch all of SFA's episodes early and ad-free on our streaming service Nebula, along with hours of bonus content like in-situ resource utilization at go.nebula.tv/IsaacArthur. As always, thanks for watching and have a great week.